In this part of the lab, we're going to work on graphing evolution, and that is going to be graphing the frequency of alleles. As you'll notice on the left-hand side here, and the frequency ranges from 0 at the bottom all the way up here to 1.0 at the top. So you can see that the frequencies will always start in the middle here at 0.5. To make it simple, but an allele frequency could start at any level. Presumably a new mutation starts close to 0 in the population. Now what I have in this drawing, I'm going to highlight for you in blue again, upper right hand corner. We have an infinite population size model, and we are working with just selection. And we're also going to hold the other 3 of the 5 fingers of evolution constant: the immigration, emigration, mutation, and random mating are all going to be held constant here. We're just looking at specifically selection and how it works in an infinite population size. Now, as the allele frequency changes across this page here, we should also write in here, these are generations moving across the bottom axis here. So this is time going across. Now, if an allele goes to 0, then it could become lost. If an allele goes to 100% or 1.0, it becomes fixed. And so those are the terminologies we use there. And I've listed on the right-hand side, I've listed 2 different groups of allele combinations. And the 2 in the, I've linked them. The 2 in the middle here will begin with these guys. Okay, these are going to be noting that if allele A1 is dominant beneficial, then allele A2, its other allele in the population, must be by definition recessive and deleterious. And so that deleterious combination is because if the other allele is beneficial, it doesn't matter how good you are, you're not as good, so relatively you're deleterious, which means bad for fitness. The other, and I've highlighted them here on the side that you can see those 2 to go together. The other possible combination of alleles is the recessive beneficial at the top and the dominant deleterious at the bottom, which we'll come back to in just a moment. So when you're doing your practices in allele A1 program, you want to repeat those multiple times. And what I'm trying to make clear here is how precise your drawings have to be. There are effectively 2 forms of the curve. Let's take a first look at recessive deleterious. We're going to graph A2 and look at recessive deleterious. I'm going to begin over here at 0.5. And with each generation, we're going to decline because we're deleterious. But as soon as you get down here around the 0.7, 0.8 area, what happens is this curve levels out, becomes asymptotic along the bottom axis here. Now, people have asked me, does it ever go to complete loss? The answer is it does, as long as the population isn't truly infinite. Truly infinite, it just goes on forever, getting closer and closer and closer. We can go down here and say it gets lost after many generations. And what we see happening here is that, and I'm going to highlight this in blue, the curve slope changed in this area because as the allele becomes more rare, more of them are in the heterozygote, which are masked by the dominant allele, and selection cannot act on them. That is significant because we know selection only acts on phenotype, not on the genotype. So when you're hiding a deleterious recessive allele, selection can't remove it. So the frequency of Q squared in this case, which is the homozygous recessive, down here it becomes rarer and rarer in the population, so selection actually gets weaker and weaker as the allele becomes rarer and rarer in the population. How about that? Now the complement of that is going to be dominant beneficial, and that's these guys here. Now what's surprising and not intuitive about this either is that dominant, but even though they're dominant, they immediately go up early on, and then it does the same form. Now it has to make the complement. Goes up here, becomes fixed. We know it has to make the complement based on the graph. We also know is when you're in this area of the curve here, when you're getting to a high frequency, again, many of the individuals that are being selected for by the dominant phenotype are actually dragging along with them a deleterious recessive allele. And so because of that, it's not selecting for a pure line, and so we have exactly the opposite of the dominant deleterious condition. So you can see that happening. Now, what do you need to be able to distinguish in your graphs? Let's take a look at the other options here, and I'm going to put these guys in green. That is the recessive beneficial and the dominant deleterious. Let's do dominant deleterious first because it seems to make more sense. I'm going to draw some lines first so you know what these things are. This is recessive deleterious here, and this is dominant beneficial here. Okay, so make sure you know those are the right two lines. And you always have to label them. Now let's take a look at the dominant deleterious. It turns out the dominant deleterious is going to go down like people might expect. It just pretty much goes right off the page here. Lost. Now that's a very straight line compared to the recessive deleterious. And even though it has a tiny little hockey stick at the end, you do not need to represent that in your drawings. Essentially what's happening is it can always be seen even when it's rare, so even the homozygote and the heterozygote both get selected out, so it goes straight to loss. Now, then we also have the converse case in recessive beneficial, which means that, there we go. Now this goes to fixation. This is because you're selecting for the purebred lines, the homozygotes, and you're not dragging along with you any of the heterozygotes that have a deleterious dominant with them, because this selection wouldn't favor that, right? So in this case, we get these two very different lines, so you should definitely be able to recognize the differences in those lines and what this means for alleles in populations. Let's go ahead and label them. If I can get A2 on here. Dominant deleterious, and I'm going to label A1. Okay, now, so these are the four different graphs that you can get. These are the only four, really, okay, from working just with selection and not with population size. Now, the inferences you can make from this. Big deal is that in this case down here at the bottom where we have the recessive deleterious alleles being selected out, we expect the population to keep in it a lot of recessive deleterious that don't get selected out. And this we see in the cases of things like cystic fibrosis, phenylketonuria, lots of conditions in human and other populations are there. The other non-intuitive thing is that recessive alleles are more likely to go to fixation than when they're beneficial than our dominant alleles. And so we have a whole bunch of things that really sort of upset the apple cart in terms of what people expect to happen in evolution. So I encourage you to experiment with this, look carefully, and think about what it means for our understanding of how evolution progresses.